His experiences are underlined by a strong academic background, 14 peer-reviewed papers, and has been working on H2S mineralization in the subsurface through the geochemical interaction between H2S and the iron-bearing minerals. Khosrow's research encompasses many aspects of oilfield chemistry: formation damage and flow assurance, mechanistic studies of scale inhibitors retention, and surface chemistry applied in petroleum engineering. Khosrow holds a BSc degree from Saman University of Technology and an MSc degree in chemical engineering from Tarbiya Modalis University, both in Iran, and a PhD degree in petroleum engineering from Heriot University in the UK. Khosrow, the floor is yours. Thank you.
For your nice and complete introduction, Julia. So, I am Khosrow Jarrahian, postdoctoral research associate from H2S University, and today it's my great pleasure and honor to present my work on the topic of research oriented towards scale management in the oil and gas reservoirs. It's basically my research in the scales that I have done since I joined H2S University. So today I'm going through the scale inhibitor retention mechanisms in carbonate reservoirs. So experimental sections, and then I move on my postdoctoral research on the modeling of FES formation, iron sulfide formation in static thermodynamic conditions, experimental sections and comparison of the experimental results and verification of my model with the experiments, and then H2S mineralization carbonate path flow testing, and I end up my presentation with summary and conclusion. So let's talk about the challenges of scale inhibitor squeeze treatment in carbonates. Which kind of challenges we are facing? So the first is the higher geochemical interaction between the scale inhibitor with carbonates. Carbonates basically, generally speaking, they have more geochemical reaction compared to the sandstone, and when the scale inhibitor as an acidic peel are injected, they can react with the carbonates, and it causes precipitation of scale inhibitors with divalent cations like calcium, magnesium, and it causes induced formation damage. This is one challenge. And the second challenge is, generally speaking, carbonate reservoirs are naturally fractured. And when scale inhibitors is deployed into the carbonate reservoirs, it's very important to be deployed in the red matrix and avoid a scale formation. But because the fractures are very high permeable zones, they can bypass from the injection to the productions, and then they can poor scale management. So this is the challenge that we are facing in the carbonate reservoirs. And now we need to understand what the mechanism of scale inhibitor retention in these kind of reservoirs. So this is the all experimental results that I have generated during my PhD. I'm not going in detail, just I am going to touch a little bit about DETPNP, theta-phosphonate scale inhibitor, phosphonate phase scale inhibitor, which is widely used in the oil and gas reservoirs. So I used two different carbonate mineralogies in my research, dolomite and calcite, with two different pH values, pH 4 and pH 6. First of all, as you can see here, from 0 to 100 ppm in two different mass volume ratios, because the adsorption results are moving along the adsorption isotherm, we have just pure adsorption. As soon as the concentration of scale inhibitor is increased about 100 ppm, the system is starting to deviate from the adsorption isotherm. It means that the retention mechanism is changing to precipitation. So for both cases, for dolomite and calcite, we've got pure adsorption and precipitation. So, and in addition, the retention of DETPNP at high pH value is higher, is greater than lower pH. It might be attributed to the highest functional group scale inhibitor available for chelating divalent calcium or divalent magnesium from the solution. And one interesting thing that we weren't expecting to get in our experiment is DETP-MP retained greater on dolomite compared to calcite. It was far from our expectation because dolomite is less geochemically reaction compared to calcite. We need to understand that. And the answer is here. So when DETP-MP is exposed to the dolomite, the final pH in the dolomite DETP-MP case is higher than calcite. It means that DETP-MP has been more dissociated and it can chelate more calcium and magnesium from solution and get precipitate. Regarding the compatibility test, for pH 4, DETP-MP is compatible with no CC water in this case, but at pH 6, it's not. So we have incompatibility issue at pH 4. So let's move on some conclusions from this part of my research. So both absorption and precipitation observed with two carbonate neurologies. However, precipitation is dominant. For DETP-MP retention, the rate is at high pH due to the escape inhibitor functional groups more dissociated for complexation with divalent cations, and DETP-MP retains more strongly on dolomite compared to calcite, right? So, what's the implications of this research for industry? This is very important to answer. What's the implication of any research for industry? Because we need to solve industry problems. So by this work, we could investigate and understand the mechanism of scale inhibitor retention and generally improve scale squeeze management in dolomite and limestone and chalk formations. This is very, very important to understand that. So now I'm moving on my postdoctoral research, modeling of H2S iron sulfide formation in static thermodynamic conditions. And then I move on the H2S mineralization. So, because of the difficulty in handling H2S in a gaseous phase, we didn't use H2S in gaseous phase. Instead of that, we generated H2S in aqueous phase by adding sodium sulfide in the system, and on the other side, we've got solution of iron. So when two solutions are mixed together, there are two scenarios. First, FES forms, and the second, FEM doesn't form. Depending on the thermodynamic condition of the system, we can have just one of these conditions. So, if we write down the chemical equilibrium equation, H2S is a weakly acid, so it can be dissociated in two stages and generate bisulfide and sulfide. On the other side, we've got iron, which can react with S2- and FeS can form. And one last equation is dissociation of H2O. H2O can produce H+, proton, and hydroxide. So if we use these notations, we've got 7 unknowns, and we can't solve and we've got 4 equations. According to mathematics, we cannot solve this equation, this system, because the number of unknowns are higher than the number of knowns. So we need to include 3 equations. So 2 equations for mass balance for sulfide, and 1 equation, mass balance for iron. I don't go in details because this is very simple algebraic operation. At the end, I've got this function. So this function has 2 variables. Again, just one function, 2 variables. It's not soluble mathematically. We need to add another equation, which is charge balance. So long story short, we've got another function with 2 variables, concentration of H+ and concentration of iron. Now we've got 2 equations, 2 variables. We can solve it numerically. So I have implemented this equation and solved in Excel sheet, and I got interesting results. So And I designed some experimental work to verify my model, if my model works properly or not. Oh, sorry. So for the first indicator is pH values of the solution. So I measured the pH of sulfide solution because the hydroxide generation, when you add sodium sulfide into the water, the pH is around 11. It's very, very alkaline solution. And as you can see, we've got a very good match between what the model is predicting and what we're observing in the lab. And the pH of the iron sulfide, the iron solution is adjusted around 3 or 4, depends on the conditions. The reason that we kept and we adjusted the pH of iron solution is to avoid iron hydroxide formation at higher pH, right? Now, two solutions are mixed, and we've got iron sulfide. And we measured the pH of iron sulfide solution. As you can see, there is a agreement between what the model is predicting and what you're observing in the lab. We need another indicator, which is concentration of iron. So we've got nominal concentration of iron, 50, 100, and 150 ppm. So we made up a solution of iron, and this is the initial concentration of iron measured by inductively coupled plasma spectrometry. And there is a good actual match between what we made up as an initial concentration of iron with nominal concentration of iron. On the other side, we measured the final concentration of iron. So there is a good match between what model is predicting as a final iron concentration and what we observed in the lab, although in some cases, in these cases, we've got over-measured ions in the system. And it is attributed to the smaller size of iron sulfide form, and basically it's because of the nature of colloidal H2S, right? So the model is working. And now some conclusion from here. Very good argument between what we observed in the lab and what the model is predicting, and the difference between experimental iron measured by ICP and the model. And the difference is because of the colloidal nature of H2S. So the implication of this finding is, nowadays we use commercial softwares, but with this method we can understand every single step of scale prediction, and we can generalize it to other type of the scales, and also it is a simple method for experimentalists to see and design the experimental methodology for their work. So now I'm going to H2S mineralization. So I prepared a sand pack. Is a mix of calcite and cyanide, 30 and 70% cyanide and calcite, and then flooded with H2S. And H2S basically is generated in the line here. And I got effluent and then analyzed effluent. So the concentration of yes. Okay. Just a bit here and then I conclusions. So the initial concentration of H2S is 48 ppm, and when the H2S is flooded into the system, the concentration of H2S is going down to 20 ppm. Some H2S is missed because of the H2S is developing into the system. I'm not going in details, and just here, the color of the pads has changed, the color of the grains got black because of the H2S formation. I don't go to SCMVDEX because of running out of time. So in this system, whatever is injected as an H2S inlet is higher than what we observe, what we produce in the effluent because of H2S scavenging. SCM index confirmed some traces of sulfur and evidence of H2S precipitate. The paths and the higher mixing ratio of the calcite with iron-bearing minerals, the greater H2S is scavenged. So the implication of these findings for industry is to capture or trap H2S and making oil and gas production safer by minimizing the sovereign and lowering H2S. So thank you very much for your attention. I know that it was very difficult to manage my presentation in 50 minutes, but thanks again for your attention. I am quite happy to take your questions.
Thank you, Constance.
Thanks.
You can breathe now. It's okay. It was a lot of stuff to present in 15 minutes, but it was really fast, so thank you, Constance, for that. No, it was good. Rightio, so I'm afraid no time for questions because we're really short of time on this one. So